Today we are going to be learning about capacitors. So this is a topic that we felt was a bit of a challenge on the AP exam, and we're just trying to make it easier for you. So we came up with an analogy to help you guys better understand these complex circuit elements. And the analogy that we came up with is a water bucket. So if we look at this water bucket here, the amount of water in the bucket can be thought of as the amount of charge on the capacitor. Additionally, the height of the water can be thought of as the voltage of the capacitor. And finally, the cross-sectional area of the water, which is a physical characteristic of the bucket, just like capacitance is of a capacitor, will be the cross-sectional area of the bucket. So with this analogy, we felt that capacitors were easier to conceptualize and easier to understand and think about when they're in a circuit. So let's do a quick exercise and let's consider what happens when we double the amount of charge on a capacitor. Alright, so one of the first things that you may notice is that the physical capacitor doesn't really seem to change. And this is true. So as you might suspect then, the capacitance does not change either. And as we can see, this holds up with our analogy as the cross-sectional area of the water does not change. However, another thing you may notice is that there's more water in the bucket. In fact, there's double, as we mentioned before, because we're doubling the charge. And this means that the charge on the capacitor or the water in the bucket is now equal to 2Q. And finally, the last thing that you guys may notice is that the voltage or the height of the water in the bucket is double the height that it was previously, and thus the voltage is double the previous voltage. With this technique, it's very easy to conceptualize capacitors and understand what happens when capacitors are put in different situations. And we felt that this was much easier than just having the teacher say to you, oh, what happens when you double the charge on a capacitor? Well, now you can visualize it, you can understand it with an analogy, with the real world situation that you 100% understand, that you're confident about, and now you can be confident about capacitors too. Here we have an example problem with capacitors. And basically our question for this is, what happens to the circuit and the capacitor as the capacitor is plugged into the battery for a long period of time? And this is a problem that might be hard for you to conceptualize at first, because you might not really have that much real-world experience with circuits, and it might be difficult for you to visualize what happens in a circuit because you can't really see where electrons are moving, you can't see the charge on something, and it's quite hard to sort of visualize if you're not as experienced. So the way we can think about this circuit is we can think about how the current is flowing. So the current starts from the positive end of the battery, and it will go around the circuit, and it will go and get to the capacitor. So we can think of the wire as something that's carrying charge, and the charge is getting deposited in the capacitor. So now we can use our water bucket analogy to sort of conceptualize what might happen to the capacitor in this scenario. We can think of the wire as, instead of carrying charge, as carrying water. And we can sort of conceptualize this circuit as a hose carrying water and depositing that water into a bucket or a capacitor. And basically we see that the water will go into the capacitor, and it will just keep on filling up the capacitor until the capacitor gets completely filled, which will happen when the voltage across the capacitor is the same as the EMF of the battery, which we know due to Kirchhoff's loop rule. that the sum of the voltage drops across a circuit sums to 0. So we know that the voltage of the capacitor will be EMF. And we know that after the voltage of the capacitor goes to EMF, that the current will, or that the circuit will not have any current through it, and the circuit will be in equilibrium. And we can actually write an equation, a function that models the filling of the capacitor. This function will model what the voltage is across the capacitor at a certain time. And this is an equation that we get from using the RC circuit equations traditionally. However, you can also sort of combine your knowledge of RC circuits with your new conceptual understanding of capacitors in order to better understand where the equation comes from and how to write the equation if you aren't 100% sure what the equation is. So the first thing we know is that the voltage of the capacitor at time t equals infinity will be EMF. So we can write that. And we know that this is going to be multiplied by 1, basically, when t goes to infinity. And we know that in RC circuits, we always have e to the negative t over tau, where tau is RC, in our equation. However, because e is raised to the negative t over tau, that goes to 0 at t equals infinity. So we write 1 minus that. And we get our equation which models the voltage across a capacitor at a certain time. And as we can see, when t is equal to 0, then we get a voltage of 0 across the capacitor, which makes sense. And when t is equal to infinity, we get a voltage of EMF across the capacitor, which, as we previously discussed over here, makes sense as well. This is a great way of problem solving to find an equation that you might not be 100% confident you know right off the bat. So this conceptual understanding of circuits that you now have will allow you to feel more confident when asked about questions relating to RC circuits or just capacitors in general.
So to understand inductors, we're going to first talk about resistors. In resistors, if you have a given change in charge going through them, you'll get a voltage. We call this change of charge current, so we can write resistance as the ratio of these two quantities. This is really useful when we're doing resistors problems. Now, let's apply the same ideas to inductors. Inductors, instead of having a voltage for a change in charge, have a voltage for a change in current. So we define inductance, which is abbreviated as L, as the ratio of these two. However, you won't see the formula written like this a lot. People will use Faraday's law and the definition of voltage in a circuit to rewrite it. When you rewrite it as Faraday's law, you get to change the numerator. And this definition is going to be the one that you see written or that people will use to describe inductors, when really this is how you should be thinking about an inductor. So luckily, you don't need to know a lot of equations for inductors. There are only 2. The first one is just the definition of inductors that we went over. The second one is also pretty easy, and it's about potential energy of an inductor. The reason that we use capital versus lowercase I is to denote whether something's changing or not. To remember this equation, you can think back to other equations from physics. All of these equations here have 1/2 times a static value that doesn't change for a certain object times a different value that can change depending on time. So current, velocity, and voltage can all change, but inductance, mass, and capacitance are all physical properties of the object. And that's how you remember the formula for potential energy of an inductor. And that's all you need to know.